Okay, so let's. So today we are going to continue this Chern-Weil theory. Of characteristic classes. So I don't know, this is lecture 2 or 3, I'm not sure, maybe 2 or maybe it's already 3. I forgot already. Okay, so recall what we did. So we had a complex vector bundle. Complex vector bundle. So the complex is important in this case. Although, I mean, we can define completely parallel-wise for real vector bundle, but the one that I'm going to discuss immediately, as we discussed last time, is for complex vector bundles. Then we define this Chern character. Chern character E. So the notation was CH of E. This belongs to even Theorem forms, where by definition this guy is just direct sums of all odd forms on M, right? I mean, even forms on M. So, I mean, first of all, it is closed. So we check this part, D of CH E is equal to 0. So then it means that because this is not a homogeneous element, it's a direct sum of all even forms, each of those forms is closed. That's what it means. Okay, so then this gives us a class. So I should not really write this. I mean, I should really write something like this, CHE. I mean, this is the original definition, but really CHE, we want to be an element of H even Theorem of M. Because it's closed, we can take its class, and this is the characteristic class, Chern class. This is the Chern form. So let me write it. This is Chern form. But this is Chern class, right? But this is by definition, again, is direct sums of all even Theorem groups, right? Okay, this we checked. This was a result of Bianchi identity, as you remember, right? Another thing is that we checked. Okay, so what was the definition? So its definition was like this: CH. I should have written this backward, but that's okay. CHE by definition we defined it to be so class of. Again, I'm a bit inconsistent here, but I explained what I mean. So this is class of trace of exponential of minus r over 2 pi I. Okay, but r is the curvature of a connection nabla on E. Okay, so let me explain a little more about this R. I mean, this looks the way we defined it was endomorphism value, true forms, and all these things. But if you fix a coordinate chart on N and a frame on E, okay, fix a coordinate chart like xi, for example, on M locally, and you fix a frame like E1, En. Well, this n is the dimension, but this n is the rank of this bundle for E, both of them locally. Then this R is just a matrix of two forms. This gives you an expression for R in this frame and in this system. So it's just a matrix of two forms. So this matrix is n by n. And this omega ij's belongs to omega 2 of, say, U. I mean, so this U is some open set that this coordinate, center of the coordinate, for example, is in U. Right? So these are two forms. So it's a matrix value 2 form. Okay. So each omega ij, in other words, you can just write as a sum, say, so here is dx mu, which dx mu, and here I put omega ij, comma, mu and mu. Okay. So there is a double index ij, just telling where the entry each entry we are taking, but each entry is a 2 form, so it has double index again, x mu x. So you see there is a 4 index notation here already, and this is of course curvature already is a 4 index object, right? So that's but ij here is between 1 to capital N, mu here are between 1 to little. Anyhow. So once you have that, you can compute it like that. And we also, now one thing that I still owe you, that the class of this guy, now, okay, again, be careful. When you write CHE, if you're being Chern formed by this, that's not a class. But sometimes people, we can put this inside, but I already understand this as a class, the quotient. So the class Chern is independent of choice of connection. You see, you had an assignment, you proved that connections always exist, but there are uncountably many connections on E. So if we don't make sure that the class, at least, the form will depend on choice of connection, but its class, if it is not independent, then you are in trouble. You don't know, you have really got something well defined. So that's very important to check this. I did not check it. I will check it later on. So book is not difficult, but it's very important thing. But today I want to introduce some more ideas around this. Okay, so this is later. But then the things that we proved was that churn of E direct sum F was equal to churn of E plus churn of F. And we also checked that churn of E tensor F is equal to churn of E times churn of F. So it's really additive and multiplicative, right? So let us see what these last two relations mean. Now, any questions, by the way? Okay. So let me now kind of expand a little bit on this last two property that we defined last time, we derived last time. These are related to K theory. I mean, it's not an absolute necessity to know this, but it's a good idea to indicate that. So connection with K-theory. I mean, to be more specific, this is topological complex K-theory. So again, let M be a compact space. Then to this space, you attach a group. In fact, you attach a ring. K0 of M. So this is called the K group of K group of M. It's actually a ring. Ring, in fact. It is defined that its definition is extremely simple compared to Durand cohomology or singular cohomology or other kinds of cohomology theory. Definition of this guy is extremely simple, but it has as much information as the other ones, even sometimes more. So how you define it? So basically, we just take vector bundles. So let I mean, this is a very temporary notation that I don't know what to denote it. So let vect M equal to isomorphism classes of complex vector bundles over M, right? So objects of this, this is a set, are just vector bundles over M. So we put all vector bundles into one bag up to isomorphism. If two vector bundles are isomorphic, we don't consider them different. We consider them set. Okay? So that's this vector. Now, what kind of a structure vector M has? So we want to understand the structure of vector. Okay? So its structure is that, first of all, this is a monoid. Is an abelian monoid. So this means that if you have two vector bundles, you can just take the direct sum, right? This is the operation. It works. And it doesn't matter, you switch around, the two vector bundles are isomorphic again.
But were you saying it's considered as a set or not considered as a set?
Say it again, please.
Were you saying you were considering the isomorphism classes of vector bundles as a set or not as a set?
Isomorphism classes of vector bundles over M it is a set, but now I'm going to introduce some structures on this set, right?
How is it a set?
Oh, how do we know that it is a set?
Yes.
Yes, that's a good question. It's not, yeah, you're worried about whether this is a huge thing that's not a set.
Oh, vector bundles, so who knows if it's a set or not.
Yeah, but we just said up to isomorphism.
It still is not clear that it is a set.
It's not clear, yeah, I agree. It's not clear, but I can give you a construction of all of them that will manifestly shows that it is a set.
Okay.
I can give you a construction. Maybe over the break, I can tell you. That's an excellent question, by the way. Yeah, we should worry about these things. Yeah, but this is actually is a set. This vector is a set. Isomorphism class of it. Okay. So now, but more structure is a monoid, is an abelian monoid. So this is the direct sum, and 0 is just M cross 0 vector space. This is the trivial 0-dimensional vector bundle over M. You can always do this. And this is an abelian monoid by this construction. But more than that, is actually a semi-ring. So semi-ring structure. It means that if you have two vector bundles, right, you can take their tensor product, as you know how to do it more or less, right? So a monoid with this, this is associative, and there exists even a unit. One is the vector bundle M cross C, so this is the trivial rank 1 bundle. Okay, so there is a unit here, and okay, so this is, but this is not a ring, so this is not K theory yet, right? But what you can do, you can always, any monoid, you can turn it canonically into a ring, into a group. So this is called Grothendieck deconstruction. So this vect M, which is just a monoid, you can actually construct a map. You can construct a group, an abelian group, which we denote by K0 of M, an abelian group. And a map from monoid, at least this is a monoid, into this monoid, in such a way that this is a universal map. I mean, if you don't know category theory, that's okay. I'm not using it. I'm saying there is a way of turning a monoid into a group, into an abelian group. The idea is very simple. I mean, I don't want to give the general construction. This is, for example, if monoid M is just, say, N. You see, this is an abelian monoid, right? So this is equal to 0, 1, 2, 1. This is with addition. You turn it into this group. The Grothendieck group of this monoid turns out to be actually, in this case, Z. So that's how mankind discovered integers from groups. They did a Grothendieck construction for natural numbers with 0 added. I mean, I'm joking. They had other ways, a much simpler way. But the thing is, this is not an injection in general. And you can think about this construction. So maybe this would, I just give it as an exercise. Give a definition of this Grothendieck construction. You can discover it yourself if you think for a few hours, or shorter maybe. How can you turn a monoid into a group in the best possible way, in the universal way, basically? You will see that you can do it. More or less. Okay, so this is the construction star. So anyhow, this general construction, once you do it to vect, you get K0, and this is the K0. And the multiplication goes through. So K0 is K group of, or K theory of M. Okay, now, so let's go back to Chern-Weil.
How does the multiplication go through?
Well, the multiplication, you just, because these elements here are going to be classes of these things here, you just multiply those classes, because this is the one, and you notice that, you check that this is independent of choice of class. So this works, basically. You check that it works. And this is part of the exercise here. Okay? Now, let's see how this Chern character relates to this construction now. So the way we define the Chern character is properties. So properties of Chern character implies that, I mean, properties, I mean addition and additive and multiplicative properties. Implies that this churn going from vector bundles, so I emphasize we are talking about complex vector bundles, okay, over M, to H even of M is a map of semi-rings. Okay, so it's just a semi-ring map because addition goes to addition, multiplication goes to multiplication, and by universal property of K groups, it just gives us a map between groups. So by universal property of K0 of M, you get a map. Again, I denote it by churn that goes from K0 of M to H even of M. So this is the essence of churn character, really. So churn character turns is a ring map. Ring map is a unital ring map from this ring in K groups to even dimensional homology. Now you might think that this side and that side could be very, very different. In fact, if you think about it, they are very, very different objects. The left-hand side is just defined based on vector bundles. The right-hand side is defined by differential forms with very, very different type of objects. But the amazing thing is that this actually has more information than this one. So if you cancel this with Q, you're going to get rational groups. But because we are in the Theorem, so let me put it in the Theorem. But if you just cancel this with R, you're going to get isomorphism in real group. So this is a famous result of Atiyah-Singer's group. I don't need it in this course for that because we just came this long, so let me just this far. I mean, let me just tell you here is a good term that this churn from K0 of M tensor R, because this is just an abelian. This is a module over Z. It's not a vector space over R. If you tensor it over R, you're killing torsion elements and stuff like that. But then this goes to H even again, the RAM of M with real coefficient, and this is an isomorph. It's a ring isomorph. So this is great, right? So the thing that we could define so easily using vector bundles, it has actually more information than all even Duran groups, so that if you tensor it with R, you get isomorphism still. So this is a very powerful result. Okay, so that's what I wanted to mention in this regard. Now, let's go back to our main thread here. So the main thread is now to define more characteristic classes.
How is the H even right?
This one?
Yeah.
So what is the question?
How is it a ring?
Oh, yes. Here, For addition, of course, you can add the differential forms, right?
Okay.
The ring structure is by multiplying differential forms, right?
I guess you also need to check that it's well defined.
Sorry?
I guess you also need to check that it's well defined because you are taking a class of forms.
Yes, but these are classes of, this is Leibniz, right? D of omega base eta is equal to d omega base eta plus minus 1 to the d of omega base eta. This shows that indeed that this is well defined. Yeah. Okay, so this is a good question again. Let me just give this as an exercise. I mean, I gave you the main hint, which is Leibniz rule. Use Leibniz. Yeah. To show multiplication is well defined. Sorry, I'm writing in a messy way because I don't want to go into the clipboard. I want to use it for later. Okay, very good.
And also then the universal property of K0M, it kind of can be just, you know, from semi-ring to ring rather than just abelian monoid to abelian groups. Yeah,
you get the monoid universal property carries to the semi-ring universal property. Yeah, exactly.
And also that tensor, what do you mean the tensor there?
Oh, tensoring over R? Yeah, these are tensors. Huh?
Is it as tensor of? Is it as tensor as rings or tensor as modules?
Oh no, these are tensors as modules, but the ring structure carries over. This is tensor as modules.
So you just change the coefficient.
You just change the coefficients. Exactly. Yeah.
Okay.
Exactly. We just change the coefficients. Yeah.
Okay.
Exactly. Yeah.
Okay.
Very good.
Okay.
All right. So now let me go to next our second characteristic class. So this is called the total churn class. So let me define this total churn class for you. So the total churn class C of E, again, C of E is equal to determinant of 1 minus R over 2 pi R. Okay. So, okay, when you think about it, so first of all, you have to unpack this definition and let's understand what this definition means. I told you that R is just, if you go to local coordinates, R is just a matrix of two forms, right? So on the IJ is two forms. So these two forms commute. So this is a determinant of elements from a commutative ring. So it's always defined. So there's no problem with taking the determinant. Same definition of determinant that you have for real matrices or complex matrices also works for determinants of matrices with entries in any commutative ring. Same definition works, same properties hold, same proofs also carries through. So that's defined. So now you can write this, you can expand this out in the following way. I mean, there is a constant term 1, and then there is a term of degree 2, degree 2 form, and then plus C2 of E, plus C3 of E, so on. Where this Ci of E's, looking at this Ci of E is now Ci of E belongs to omega 2I of M. So this is a 2I form. I mean, you just write down the expansion of this in terms of elements here, and then you notice that you're going to get a 2I form, and then 4, and so on, as you move on. Now, one thing that's not clear is that, so these are called the Chern classes. I should say the classes of these things. Again, there is a little bit of, I mean, not right now, I mean, so let me define these things actually. They're called Chern classes. All I have to make sure is that these guys are actually closed. This is not clear from our definition, right? From the definition that I give you, this is not clear. And the reason that's not clear is that I had a very general result.
How is that in the Dirham cave forms? The determinant of this curvature thing, I mean, you took the trace and it is in the Dirham, but then before you took the trace, how is it in Dirham?
I'm not taking the trace.
No.
I'm not taking the trace. I just directly work with R.
But R is with coefficient in E.
No. R is imagine R is a matrix. So just go to a local frame and this is okay. R is a matrix of two forms locally.
And these two forms, they are in the Dirham?
These two forms are locally defined.
But is it like the usual Dirham?
Yeah, the two forms are differential two forms, yes. The two forms are, yeah.
This is last time you defined it with coefficient in the vector bundle.
No, but these are, once you go to local frame, it becomes, because endomorphisms are matrices and this becomes that too. But now let me just tell you that what is not clear is why these are closed. So recall what we did before showed that any class of the form trace of f of R, where f belongs to C of x, any power series ring, right? Any power series is closed. D of trace of f of R is equal to 0. Remember, this was a consequence of Bianchi identity, right? From last lecture. And this we directly applied, so e.g., we took, for example, trace of exponential of minus R over 2 pi I, right? That's what we did for Chern character. But here we are doing something totally different. This is not a trace. This is a highly nonlinear operation. You're taking determinant. And yet, I'm claiming that this is closed. So this proof of that the terms here is closed is not obvious. So the proof of closeness, so how to show closeness here? So let me now tell you, let me give you the lemma, then I will prove the lemma. Right, lemma. C of E is a closed, non-homogeneous, is a closed, non-homogeneous for proof. This proof is based on some very interesting identity. There is a matrix identity. So the matrix identity I want to use is the following. It's determinant of 1 plus R is equal to exponential of trace of log of 1 plus R. Okay, so this is a very interesting matrix identity, right? This is for any R belonging to n by n matrices from coefficients. Actually, the entries of the matrix could be from any commutative ring, actually. Any commutative. Commutative is important, otherwise we cannot take determinant of a non-commutative matrix, elements from a non-commutative ring. Okay, commutative ring. Okay, so let me first indicate the proof of this, and then I will show you how ideas that we used can be obtained to prove this. Okay, proof of a star. Okay, let's first do it for n equal to 1 and a equal to r, for example. But you can do it for any. But what is in that case? We are just saying that 1 plus x is equal to exponential of, because the determinant is just the same, is an exponential of, and there is nothing in trace. It's a trace of number is just a number because it's a 1 by 1 matrix, and this is just log of 1 plus x. Of course, this is absolutely correct. So there's nothing to prove here, right? Okay, so that's good. Now let us do this for diagonal matrices. Oh, no. R equal to x1, x2, xn is diagonal. Let's see what happens. Determinant of 1 plus r is, of course, is equal to product of 1 plus xi. Right? Now, what is on the right-hand side? Exponential of log of, oh, no. Exponential of trace of, I want, trace of. Now, log of 1 plus r, you see 1 plus r is also diagonal, so log of the diagonal is going to be a diagonal matrix. So it's going to be like log of 1 plus x1, log of 1 plus xn. Okay, so this is left-hand side. Right-hand side is this one, so this is equal to x of. Now, trace of this thing is sum of log of 1 plus xi. Okay, so of course this is nothing but you see it's just a product of 1 plus xi. This is equal to left hand side. So for diagonal matrices is also true. Now I want you to convince yourself that this is true in general by bringing this, by diagonalizing. Okay, so the exercise is to the general case. I mean, do it for A equal to not any ring. I mean, just don't go to general ring. Just do it for R or C. Okay? Do the general case for R and C at least. Okay, you notice that you can diagonalize, but then not all matrices are diagonalizable, but you will notice that those matrices that are diagonalizable form a dense subset in the space of matrices, and you argue that this is equality is true. Both sides are continuous functions. They match on the dense subset of that space, so they match everywhere. So there is a density argument you can finish. So we will discuss this in tutorials or something like that. So this is the end of my proof of part star. Now let me tell you that star actually shows that that CE is in fact is a closed form. That's what I need, really, right? Okay, so here. D of C of E is equal to 0. So by what we know, this guy is a closed form, right? This trace of log of 1 plus R. It's like of the form trace of f of R, right? This is closed. So now all you have to convince yourself is that if you have a closed form, if you exponentiate it, you're going to get closed form. So show that if omega is a closed form, right, then exponential of omega is also closed. So in other words, I'm saying d omega equal to 0 implies that d of exponential of omega is equal to 0. Okay, so how can you prove that? Well, I mean, what is exponential of omega? Exponential of omega is sum omega n over n factorial, right? If you want to take its d, you just apply d term by term. Now, what is d of omega n? Well, d of omega n, you can argue it's just like this. You see, use Leibniz. I mean, this is like d of omega n times. I mean, I should say maybe k, because n was the dimension of the manifold. I don't want to use it here. K, so k factorial, so k, and here is k. So now Leibniz says that this is equal to d of omega times omega. Well, but d of omega is 0 plus omega times d of omega but this is 0 plus omega times omega, finally d of omega. This is k minus 1 times, right, each time, and there is this one begins. So the whole thing is. So this was an interesting proof, because I could not directly prove that I just used this result that I proved last time. plus this interesting combinatorial identity between exponential trace and log. And then we can just prove that. Okay, so now there is something very interesting. So this closed forms, they define classes, and this is called the Chern class. Okay, so here let me give you the definition. Let E over M be a complex vector bundle. I emphasize again, we are over complex numbers. Its Chern class don't confuse Chern classes with Chern characters, okay? These are related but very different objects. Its Chern class, Ck of E belonging to H to K is K doubled here, right? The RAM of M is defined by, well, basically that's the equation that I wrote, right? Determinant of 1 minus R over 2 pi I equal to C0 of E plus C1 of E plus C2 of E. But C0 of E is already 1. We know that. This is just 1, but this C1 is the first Chern class, second Chern class. Okay? So that's the definition. Now there is now you may wonder what are the algebraic properties of Chern classes, for example. Is it multiplicative? Is it additive? What kind of properties it has comparable to properties of the Chern character, for example, right? So let me just make some.
So here the determinant is not the usual determinant.
Determinant, what do you mean?
Because the big trace is also not the usual trace of matrices. So your determinant.
What do you mean? What do you mean not usual trace?
Oh, I probably should think a bit more.
Yeah, that's okay. But what I invite you, the way to think about it now is the following: R is a matrix of is an n by n matrix. The entries of matrix are two forms. You can just simply write that matrix if you fix a frame on your bundle and a local coordinate on the base. Locally, you can, again, I emphasize, locally you can always write R like that, and that's what it means. Now you might wonder, what if I choose another coordinate chart, and what if I choose another frame? Well, the thing is that this, if you change frame, it goes to R prime, but this R prime is going to be something like G R G inverse. So if there's always some conjugation. There's always some conjugation, so this determinant is invariant under conjugation because determinant is as in trace. I know you're worried about the original definition of trace that we had last time.
Yeah.
But if you think about it like this, you don't even have to think abstractly as you know that, like last lecture. But this is a good way to think about it, right? So now let me make a comment here. My comment is that I mean, this is not. So what I'm saying is that what I'm trying to say here. Let me just gather my thoughts. Yeah, churn class, I mean, total churn class is not additive. It's not additive. In other words, C of E direct sum F is different from C of E plus C of F. Remember, for Chern character, we had additivity, right? Why? This was the case, but this is not the case. I mean, if you go through the definition of determinant, determinant of direct sums of two matrices, I mean, stack them one over the other, that's not going to be additive, right? It's not. We have a beautiful formula called Whitney sum formula. Whitney sum formula. In other words, I'm saying that C of E direct sum F is equal to C of E times C of F. Or maybe Whitney product formula, I should say. Or Whitney product formula, yeah. Well, if you emphasize on this one, you could say sum. This one we say product, but okay, so it's called, I believe it's called Whitney product formula. And this is the one. Now, proof. Now, the proof is very easy if you look at this definition. Why? Because, so peak connections number 1 and number 2 on E and F respectively. So maybe I call it nubla E and nubla F on E and F respectively. So then nubla E direct sum nubla F is a connection on E direct sum F. I mean, if you go through the definitions, this perfectly works. You can even talk about matrices stacked over each other. So this implies that the curvature of this, R of this E direct sum F, is actually a matrix which is like this. Block diagonal, so here is curvature of R, here is curvature of F. The block diagonal matrix. Okay, so we have got a block diagonal matrix like that, and we want to feed into this formula, but look, I mean, the determinant of block diagonal matrices multiply, right? I mean, determinant of 1 minus R E direct sum F over 2 pi I is equal to determinant of now huge block diagonal 1 minus RE 2 pi I 1 minus RF 2 pi I. But then multiply, right? So this is determinant of 1 minus RE pi I times determinant of 1 minus RF pi I, right? Okay. And this is, of course, the total product of total Chern classes on the right hand side. This is CE times C. Right? So this Whitney product formula is very important because it tells you what happens under the direct sum. So if you expand this in some more kind of, so this is really like 1 plus C1e plus C2e times 1 plus C1f plus C2f. Okay, so remember, this is degree 0 form, this is degree 2 form, this is degree 4 form, so on. So when you expand it, again, you can collect terms of the same degree together, and then you know what's going on. So this is like 1 plus. So terms of degree 2, there are only 2 terms of degree 2. No. There is this C2e plus C2f. If you multiply this by that, you get C2f. Oh, no, sorry. This is nonsense. I'm sorry. This is C1e plus C1f. Yes. There is no other degree 2 term, right? There's no other degree 2 term. This is the one and this is the one. And then degree 4 terms is going to be C2e plus C1e, C1f plus C2f, and so on. So it's a little bit like product of power series or polynomials. The terms of different degree multiply give you the same degree if you match the terms. So now you can say, for example, what is the second Chern class of direct sum, right? The second Chern class of direct sum is second Chern class of E, second Chern class of F, plus first Chern class of E times first Chern class of F. So let me write it down because this is kind of knowledge maybe. So C2 of, for example, so let me write C1 of E direct sum F. This is additive, this is fine. But from C2 things gets complicated. So it's going to be C2 of E plus C1 of E, C1 of F, plus C2. So I think it's a good time to take a break now and for 10 minutes, and then we come back and continue. Okay, so let me stop and then we can, okay, pause. Yes, notice recording. Okay, so let's do a simple application. If E has a number 0 section, then Ck of E equal to 0, where K equal to rank of, remember, rank of a vector bundle is dimension of the fiber, but this is complex, so rank equal to dimension of a fiber of X over C. I mean, we are assuming N is connected, so this dimension doesn't change point to point. So this is a vector, complex vector space. Take its dimension. This is called rank of the bundle. All right. So yes. Okay. How do we prove this now? Proof. So this E, this vector bundle has a nowhere 0 section. So you can take that nowhere 0 section, define a subbundle, right? So let S be this nowhere 0 section. I mean, the section is continuous at least, right? Or smooth, doesn't matter. It's continuous at least. Nowhere 0 section of E. So Well, I mean, this is like S goes from M to E, right? So S of M belongs, I mean, it's different from 0, and this belongs to EM for all M, right? So this is how you think about these things, right? So at each point you have a vector that could change, but that's basically what it is, section. Now you can use this section to define a rank 1 subbundle. At each point, the bundle is generated by this vector, right? So let E1 subset of E rank 1 subbundle defined by S. So the fiber of E1 at any point M is basically C times S at M. So you take this one-dimensional subspace generated by this non-zero vector at that point, you call it E1, and so on. You cut down a one-dimensional subspace point to point. Okay, now let EK minus 1 inside E be this complementary subspace. Okay, be the complement bundle. I mean, by this complement bundle, I mean the following. So you can decompose any fiber as direct sum of these two fibers, E1 at M. Direct sum, you can choose a complement, but you have to choose it in a canonical way. I'll tell you how to choose this. E1M plus direct sum EK minus 1. So the question is how to choose this, because you have many choices, right? You can define the best possible choice by putting a metric and then orthogonal complement on this. So wait when I discuss metrics and inner products on bundles, then we'll discuss it. So e.g., so let me just say e.g. define an inner product on E and let say EK minus 1 equal to orthogonal complement of E1. I mean, fiber-wise orthogonal complement, of course, right? This is just everything is in the family. Okay, so you manage to decompose your bundle now as direct sums of two bundles, E1, direct sum EK minus 1. This is rank 1, this is rank K minus 1. But notice that this guy is trivial because it has an over 0 section. This is a trivial bundle, right? So it's so this is a trivial bundle. So the total Chern class of this guy is just 1. It's just rank of E. I mean, C1 of E1 is 0 because it is trivial bundle. So we can just apply the Whitney sum formula, Whitney product formula. The total Chern class of this guy C of E, which is equal to C of E1 direct sum EK minus 1. So that's equal to C of E1 times C of EK minus 1, right? So now we have got equal to 1 times C of ek minus 1. Okay, so you notice that this is equal to now Ck minus 1 of ek minus 1 plus lower order forms. So there is no form of degree 2k, right? So this implies that this top form here is 0. Ck of left-hand side, because it starts with k minus 1. So now here is so if for some reason you know that the K-Chern class is not 0, then you know that your bundle doesn't have a nowhere 0 section. So you can read it backward. So if these are kind of typical applications of characteristic classes. If you know that Ck of E is different from 0, the E admits no non-trivial section. I mean, these are kind of, it gives you alternative approach to proving that there are nowhere 0, for example, vector fields, but this is much more general, much more powerful idea than original proofs of Ball theorems and this sort of things. Anyhow, this is a very simple, meant to be a very simple thing. Now, let me just one comment about functoriality, which is very important. So this is an important comment. Functoriality. So imagine you have a map from manifold to manifold. So a smooth map. I mean, first of all, you can do a construction called pullback bundle. E over N, a smooth bundle. So there is this construction called pullback bundle. So this is called F star of E. So this is over N. So the situation is now like this. So we have got E, this is N, this is F, this is M, here is F star of E. So bundles pull back always. They don't push forward, they pull back. So bundles, so the slogan is bundles pull back. In general, you cannot push forward a bundle. And in general, don't push forward. This is just in the nature of things, I mean, so to speak. I mean, in general. So how is this defined? Well, definition of F star of E is very easy. That's equal to basically the set of all M and C belonging to M cross N, such that F of M is equal to, so this is pi of C. This is projection. Okay. So you may want to check for yourself that this is a bundle. This is a bit, maybe, it needs a proof, but it's not so bad. There's also a map here. You can complete the diagram like that. And second of all, you can also check that connections also pull back. So this is a bit, needs a, so if you have a connection nabla on E, you can define f star of nabla on f star of E. I'm going to give you this as an exercise to prove. I don't think I will assign it, but I want you to think about it. Exercise, prove this. You can also read it in many references, also in books that I suggested. So that's all. So you can pull back. And using this, then you can show that so using 1 and 2, implies functoriality. For example, you show that if you take a Chern character of this, Chern character of E, is like Chern character of f star of E. Also, if you pull back Chern class of E, the total Chern class, this is like pullback of, it's Chern class of the pullback. Now, here, the only thing that I did not define here, maybe I should have had another item which would be 3, and then I would say 1 plus 2 plus 3 implies this. 3 is that the pullback of differential forms. You see, if you have a form on differential form on N, and you have a smooth map like that, you can pull it back. Form on N. So let me define this operation because it's very easy. That's a generalization of pullback of functions actually. So how does it? I'm using too many stars here. Too bad. Maybe A. How A is defined? Definition is very easy. So you have imagine locally. So choose like local coordinate charts. I mean, so choose a form locally. Right. Omega, this is omega, as this something like, like sum fi dxi1 wedge dxip, I1 ip, I1 ip. Locally, you can write a p form like this. And what is f star? What is f star of omega? So basically, what you do, you just replace these variables by the corresponding variables here. So if x is equal to f of y, you just replace x by f of y. That's just you just write sum I1 IP f I1 IP just because there is an x here, right? Then you write x as f of y. And here xi1 also, these are n components here and there are m components. You just replace by these things and then you just say dy I1 wedge p I y. This becomes completely mechanical operation. If you think about it, it has a deep meaning, of course, but doing it is quite straightforward. And this is the pullback of forms. So 1, 2, 3 gives you basically this. So this is very important. It means that this construction of characteristic classes is functorial or is canonical. If you do some construction over here, and you have such maps, you can do this construction, put them back here. So that's This is very nice. Have this in mind, please. That's very important.
How come is it called functoriality?
Oh, yeah, because it's functoriality means that we know how to pull back objects, how to pull back morphisms between objects also. I mean, this is a way of referring to this as functoriality or being canonical, yeah. You can think of there is a category of vector bundles, for example, over some basis space, and this Chern character is a functor from that category into something else. But I don't want to get into too much categorical construction, but that's essentially, it means everything is natural, yeah.
Hmm. So it's basically the F would deduce a natural transformation.
It is a natural transformation, yes. That's right. It's a natural transformation between two functors to be.
Yeah.
Yeah. I mean, K theory is a functor, the Ram cohomology is also a functor, and this Chern character is a natural transformation between these two functors. But I don't want to get into that just with. And also, Chern class is also a natural transformation. Yes, exactly. That's very good. Excellent. Okay, so now let's go to gymnastics of these constructions because there was a question about relation between Chern class and Chern character. So let me tell you, this has to do with the issue of Chern roots. So let me just. Chern roots. So this is a kind of fictitious object. So introduce kind of, let me put it like this, fictitious. I call it fictitious objects, x1, x2, xk. K is equal to rank of E, such that determinant of 1 minus r over 2 pi I is equal to product of 1 plus xi, from 1 to k. Of course, I mean, this is like roots of this characteristic polynomial, right? This is a kind of similar to idea of characteristic polynomial. These are like roots of this characteristic polynomial. But in reality, this R is just a matrix of two forms. So we are not really allowed to have these things as numbers or as some sort of forms or anything. These are just some fictitious objects, but otherwise, these are very, very good, things to have in mind, because this you can write it as 1 plus sum of xi's plus sum of xi, xj, I different from j, plus so on, right? Sum of xi, xj, xk, I different from j, different from k. And the last one is just product of these things. So now, in other words, these guys are just elementary symmetric functions in these variables x1, x2, xk, right? So these are just elementary symmetric functions. Okay, now, okay, so C0 of E, of course, as we saw, this is 1, this is this term. But this term is C1 of E, right? So C1 of E in terms of this Chern roots are simply some xi, this is like sigma 1 of x1, xk, sorry. C2 of E is sum, again, xi, xj, I different from j, that's equal to sigma 2 of x1, xk, and ck is product of xi, that's sigma k of x1, xk. Now, these are the things that we have seen in algebra. These are called elementary symmetric functions, right? So remember the fundamental theorem of fundamental theorem of symmetric functions. You remember that from like field theory course or from basic algebra? We call the fundamental theorem of symmetric functions. So we saw that these symmetric functions, I would say C or R of x1, xn symmetric inside R of x1, so xk here, sorry, xk. So this was the idea that for any commutative ring or the ring of symmetric functions over R with coefficients in R, right? This is the ring of symmetric functions with coefficients in R. What is that? That's really all polynomials, symmetric polynomials, polynomials that are invariant under the action of the symmetric group over this value. This is a subring. This ring is actually, this is isomorphic to the ring, again, of polynomials in n variables, but in these things, in sigma 1, sigma k. These are the elementary symmetric functions, right? So this is the fundamental theorem. This was essentially proved by Newton. So this is Newton. There is another basis here. If you assume that your ring R has characteristic 0, characteristic of R is equal to 0. By this I mean, I really mean if 1 over n belongs to R for all n. That's what I mean, really, because this is a ring, so defining characteristic. But that's what I mean. Then there is another basis, a new basis, which is these power sums, right? Power sums. So P1 of x1, xk is equal to sum of xi. P2 of x1, xk is equal to sum of xi squared. P3 of x1, xk is equal to sum of xi all to the power 3, and pk of x1, xk is equal to sum of xi to the power k. But this condition is needed in order to write a general symmetric polynomial with coefficients in R in terms of these power sums. So then we can just show that R of x1, xk symmetric is isomorphic to this ring again, but it's just in terms of this variable. So this is R. And there are these famous Newton relations that relates this basis, ring basis, to this basis. Newton relations. So express Pi in terms of sigma I and vice versa. Why this is relevant here? This is relevant because it's the relation between Chern character and Chern classes. You see, Chern characters have to do with this. You see, we define Chern character of E to be equal to trace of exponential of minus R over 2 pi I, right? I mean, if you just write this down, this is sum of trace of minus R over 2 pi I, right? To the power, say, m divided by m factorial, m from 0 up to infinity, right? And this trace of the rth power of a matrix in terms of these Chern roots, you can just write it as powers of these xi's. So that's equal to sum, basically now, yes, 1 over minus 1 over 2 pi I to the power m divided by m factorial times x1 to the power m plus xk to the power m. And this is m from 0 up to infinity, right? So these are Chern roots. While, on the other hand, the Chern class, total Chern class, is just the sum of these things. I mean, elementary symmetric functions. So you are in the other basis. You are in this good basis, sigma i's, right? This is equal to sum of ci of E, I from 0 up to k. That's equal to, yes. Or maybe I don't need it here because I already chose that. Most probably I don't need this factor because I defined the determinant of 1 minus R over 2 pi I to be equal to a product of 1 plus xi. Yes, I don't need this factor. 1 over m factorial, this is good, this is good, yes. So this is equal to 1 plus x1 plus xk plus, again, x product of xi, xj, I different from j. Okay, so so to answer your question, then the relation between Chern character and Chern classes is the relation between the two bases of a space of symmetric polynomials. One basis is the power basis, that's related to Chern character, and the other one is elementary symmetric function basis, that's related to Chern classes. And if you go from one to the other, you express Chern character in terms of Chern classes in terms of Chern character. So let me give you a simple exercise or example. Any questions so far? Okay, so let me just do something here. Okay. Yeah, I mean, this is really very, very classic old stuff. This is Newton, really. 1670s. Yeah. Yeah, Newton in his private notes notebook, he was saying that when I got bored, I did these calculations to get rid of my boredom. So he He said, I won't tell you how many hours I spent doing these calculations and enjoyed it, something like that. Anyhow, so let's do C2 of E, for example. Second Chern class, which is equal to sum xi xj. I different from j. You can write it as sum xi squared minus a sum xi squared, right? Now this is of course is C1 of E squared minus this is this guy trace of minus r over 2 pi I squared. I mean, this is the second component of the Chern character, right? So if you write Chern of E2, I can write the second component of the Chern character. So I can just write Chern character. Remember, it's not a homogeneous form. It's like 1 plus first component. This is degree 2, which is C1, by the way. That's not different. That's just trace of this guy. Plus CHE2, so here is 2. So this is the degree 2, which we raise this to power 2. And so on. So the corollary is that Chern of E is a polynomial in several variables. Of course, I don't mean one variable is a polynomial in Chern classes, and vice versa. You can just like using variables. Okay. So one more class today, which also is new. This is, let me define the Todd genus. Any questions about these things, by the way?
Maybe could you explain the last line just a little bit?
This one?
Yeah, the polynomial.
Chern of E is a polynomial in Ci of E. Yeah, this is the Chern character is a polynomial because Chern character is a polynomial in these guys, in these powers, right?
Mm.
And the powers, you can always write it in terms of elementary symmetric functions because the powers are symmetric polynomials.
Okay.
So every symmetric polynomial can be written in terms of elementary symmetric polynomials, so can be expressed in terms of those Chern classes, right?
Mm.
Now, the good thing about this basis sigma, so we have two bases, pi and sigma I. The good thing about basis sigma I is that it works over any ring. For the basis pi, you have to divide.
Okay.
Yeah, so there's a, but that's why Chern character is only a rational form, is not an integral form. But Chern classes are integral forms. I did not mention that, but I will mention it later soon.
Okay.
Yeah, very good. Very good. Any other questions? Okay, now let me define something very interesting, and this is new then. This would be Todd genus. Yes, state for complex vector bundle. We are going to use these things towards index theory because the formula of Atiyah-Singer involves these characteristic classes. So Todd genus. So again, let E over M be a complex vector bundle over smooth manifold M. So let us define Todd E. The Todd was, of course, a mathematician, British mathematician, I believe. Todd genus of E is the class Todd E, I guess, E is equal to determinant, oh sorry, which is equal to determinant of, so let me write it like this, x over e to the x minus 1 at x equal to minus r over 2 pi I. Okay, so yes. Okay. So again, just write it as determinant of this matrix minus r over 2 pi I divided by e to the minus r over 2 pi I. Yes, yes, yes. Okay, that's fine. Minus r over 2 pi I minus 1. Okay, so this belongs to H. Again, it's going to be an even form. So go on. So let's try to unpack this formula, see what it means. Okay, so what do we mean here? Well, let's look at x over e to the x minus 1. X over e to the x minus 1. What kind of power series is this? X over e to the x minus 1. Well, you see, x over e to the x minus 1, it may look like it has an ambiguity at 0, because if you put x equal to 0, you get 0 over 0, right? But you can use L'Hopital to get rid of to compute the limit. Actually, this is equal to 1. I mean, this is a nice function at 0. So, so as a result, you can just write it as sum Bm over m factorial, x to the power m, m from 0 up to infinity. So there is a power series expansion. So this is Taylor series expansion at x equal to 0. I mean, this is a very nice analytic function, actually, at x equal to 0. Now, these BMs are called Bernoulli numbers. And Bernoulli. I want you to show that, so there is this exercise. I want you to show that P0 is equal to 1, B1 is equal to minus 1/2. And I want you to show that all odd powers, odd values of Bm is 0. So in other words, B to k plus 1 is equal to 0 for all k bigger than or equal to 1. I mean, for k equal to 0, this is not 0 minus half. But for all k bigger equal to 1, B2k plus 1 is equal to 0. So these are the famous Bernoulli numbers. This was done by Jacob Bernoulli. Was it Jacob? I think it was Jacob. Yeah. Jacob Bernoulli. The big brother, the first one. The guy who actually was the initial leader of the clan, that clan of mathematicians, Bernoullis. Right. So that's okay. So once you know this, then what do? You just replace x by this guy, and you have a series. But now you have a matrix, and then you just take a determinant of this matrix. Okay. So this looks like a very complicated object right now, but it will come handy soon. At the moment, I don't have much more to say. That this is a kind of is a genus what means in general. There's a definition, and there's a reason that this was introduced. It has some nice topological properties that we will discuss it soon. So this is the end of the thing. So on Monday, when we come back, we will discuss characteristic classes of real vector bundles, which we need also. These are Pontryagin classes, a hat genus, and basically that. And then we need one more, which is Euler class. Euler class is more familiar, but yeah. So we'll look at that, and then yeah. Basically, if you want to read up some stuff, try to read from any source you want a little bit about Pontryagin classes in this Chern-Weil picture and a hat genus. That would be very good. Okay, so I think I'm done for now. So we did a good thing. So let's stop and then.